Okay, let me start now. Are you able to see the screen? Are you able to see this slide?
Yes, sir.
Okay. So last class we had covered to this slide, right? So where I was talking about relation between the Z transform and the Fourier transform. So we said that Z is a complex number or a complex quantity, and it is actually a complex exponential. So it is a general form Z equal to R into e to the power j omega. So if you are evaluating the DTFT of x of n, so this is how like we connect the Z transform and the DTFT. DTFT transform, which may not do well. So you're able to see the screen, right?
Yes, sir.
So let us move forward. So Z transform consists of like three different parts, I would say. So initially we would cover bilateral Z transforms, and then we will think of the inverse Z transform. How to take the inverse Z transform without using the contour integral. That is how to use partial fraction expansion for Z transforms. And then we'll come to unilateral Z transforms for solving difference equations. And the last part of the topic would be how to interpret the frequency response of a system by looking at poles and zeros of the transfer function. So if you introduce a pole or a zero, what impact does it have on the frequency response? So because we will talk about the system transfer function h of z, so we need to understand the frequency response of that system. So the impact of poles and zeros on the system transfer function is something that we will look at the end. That is a complicated part of the chapter. The Z transform chapter is a slightly involved chapter. There are connections between Z transform and the Laplace transform. Are you all able to hear me? Everyone
Yes,
is
sir.
able to hear me?
Yes, sir. Yes, sir.
Yeah. So we will look at what is called the region of convergence. So in the Z transform, we have an extra thing which is called the region of convergence, because this Z to the power minus n, it has a tendency to blow up. Okay. So the region of convergence will exclude all poles. So h of z can become infinite when you have a pole. So we have to worry about poles, and we have to see what a pole does or what a zero does to the frequency response of a system. So we will analyze this in detail. And the next chapter that I would take is the frequency. analysis or the frequency response analysis or the frequency domain analysis of LTI systems. So there we will look at more details, study of the phase and the phase spectrum and the amplitude spectrum of filters. So existence of the Z transform. So we have this as infinite series. This infinite series is supposed to converge. So for limited, time limited and bounded signals, that is something like this, which is shown on the right hand side. But the time limited signal, it is 0 for some n0 greater than 0, and it is again 0 for n0 less than 0 or negative n0. So beyond below some threshold, it is 0 on the negative axis, and above some threshold, it is again negative 0 on the positive axis. So this is a time limited signal, and the amplitude of the samples is bounded. That means it is not infinite amplitude signal. So for these kind of signals, the Z transform will always exist, and uh, the left hand side of this summation will always be finite. But there can be peculiar cases where this will not happen. So we will see different types of signals. We'll analyze different types of signals. One is a right hand signal and the other is a left hand signal. So the right hand signal is something that is 0 for some n less than n naught. So if you see the first figure, can you all see the cursor? First figure is a right hand signal because it exists only on the right hand side, and it is 0 for some n less than n naught. N naught is positive here. Okay, this n naught can be something like 1, 2, or 3, whatever. So it is 0 below this and positive beyond this. Similarly, a left hand signal, it exists only on the left hand side of a threshold n naught. Okay, so XL of n is equal to 0 for any n greater than n naught. So these are two types of signals that we will be looking at, and we can have various types of signals coming in. Easiest signals to analyze are exponentials. So we will have something like this: alpha to the power n u of n minus n naught. So u of n minus n naught means a signal that is uh, towards the right hand side, and it is positive beyond n naught. So alpha to the power n u of n minus n naught. So switching action happens at n naught. Similarly, we have the left-hand side signal, a left-hand side exponential, that is beta to the power n u of n minus n naught, or rather minus n plus n naught. That is u of n naught minus n. So u of minus n means a step towards the left-hand side, and minus n plus n naught means something that is shifted to n naught here. N naught is a positive number here. So you can imagine that n naught can be a negative number also, so it will start from somewhere here. Okay. So this is the typical signal that we will analyze. So, and we will think about where the Z transform converges for the infinite series. So when I calculate x of z using the infinite series, over what region of the Z plane this will converge, and over what region of the Z plane it will not converge. That means it will diverge. So this infinite series has to be analyzed analytically, that is using mathematics, and we are supposed to find out the expression, the closed form expression of the infinite series. So we will use the geometric progression formula, so we'll look at that. So various types of convergence are ROCs, what is called the region of convergence. You would have come across this region of convergence while studying Laplace transforms. Okay. So one type of region of convergence that we will look at is a circular region of convergence. So everything will within a certain radius, uh, that region of the Z plane is said to have numbers or complex numbers over which the Z transform will converge. So a disk with center 0 and radius r is the set of all complex numbers Z satisfying this condition, that is the magnitude of Z is less than r. So if you compute the magnitude of all the complex numbers lying inside this shaded region, they will be less than this positive number r, and for such z- complex number z, only h of z will converge. So that is the type of ROC that we will look at. Another ROC that we will look at is the annulus. That means the numbers or the z-plane numbers or complex numbers lying in a in an annular region around the origin. So something which is beyond R0 and less than R1. The magnitude of the complex numbers in the z-plane will satisfy this inequality. So z is greater than R0 and less than R1, where R0 and R1 are real constants, and R0 is greater than 0 and is less than R1. So this is the z plane over which you are going to evaluate x of z or h of z, whatever, and you are going to see whether for those complex numbers which are only in this shaded region, the expression will converge, otherwise it will diverge. The last type of the ROC is the exterior of a circle. So mod z is greater than R. So we'll see for which kinds of exponentials, whatever I showed you, and what kind of discrete time signals, these three different ROCs will exist. So I will show you some examples, and using those examples, you can understand that how each ROC will occur. So the Z transform is like a lock and a key. Okay. So the lock is something like the expression for the Z transform, and the mathematical expression for the Z transform, and the key is the ROC. So if you don't have the ROC information, you cannot understand how the signal will look in the inverse domain, that is in the time domain. So somebody gives you the Z transform of a time domain signal. Yeah, please, whoever's mic is on, please mute it. Okay, so whenever you are given the Z transform expression, you want to find out the inverse Z transform and go to the time domain uh, and want to see how x of n looks like. So you cannot do it unless you are given the ROC. So we have to be careful in Z transform. We were not talking about the ROC in the DTFT. Okay? So here we are talking about the ROC. So let us look at the first uh, type of complex exponential. So u alpha to the power n, u of n minus n naught, where alpha can be a complex number. Okay. So x of z is given by this bilateral z transform, and it can be now written. You can change the lower limit from n naught to infinity, because u of n minus n naught is a shifted unit step function or unit step sequence. So it is something like starting from positive n naught. If n naught is greater than 0, then it starts on the time axis at positive n naught, and so we can now make the lower limit as n naught to infinity. So if you now simplify, this is alpha to the power n into z to the power minus n. So you can write it as alpha into z to the power minus 1 whole to the power n. So if you see this, it is something like alpha by z. So it goes as alpha by z plus alpha by z whole square plus alpha by z whole cube, like that. It is an infinite series going from n naught to infinity. So if the series will converge, we will see that the expression how it will come. I will derive all this and show you. So if the series converges, and it converges only when alpha by z is less than 1, we will see why that thing happens. That means mod of z is greater than alpha mod. So uh, the series will only converge when mod of z or the magnitude of the complex numbers on the z plane for which this series is getting evaluated will satisfy this inequality, that is mod z will be greater than mod alpha. So if you have the ROC will be something like beyond a certain radius. So this is mod alpha, this is the magnitude mod alpha. So all z beyond mod alpha will be in the region of convergence for this x of z. This is the expression. So this left hand side will be less than infinity, or the magnitude of left hand side will be less than infinity for all complex numbers beyond this circle of radius mod alpha. So the path of integration for the inverse Z transform, that is whatever we have shown, the inverse Z transform can be calculated using this contour integral. You can see this contour integral here. Are you able to see my cursor?
Yes, sir.
Yes, sir.
So the inverse Z transform requires a contour. Okay, this contour is supposed to be centered at the origin and having some radius such that the contour lies inside the ROC. So if you are going to, sorry, so if you are going to use the inverse Z transform formula to calculate x of n back, then you are supposed to use the contour which will be lying in the region of the Z plane outside the circle of radius alpha, that is inside the ROC. So that is the care that one has to take. The next exponential, whatever I had shown you, beta to the power n u of n naught minus n, or minus n plus n naught. So this is this kind of a signal. This is a signal. It's a complex exponential rising on the left hand side, starting from n naught. Just hold on 1 second. Let me take this call. Yeah, so let us continue. So we were looking at this complex exponential which exists only in the negative x-axis. And we want to now find out its Z transform. So we can see that capital X of Z is equal to summation n equal to minus infinity to n naught. That will be the index of summation, and it will turn out to be beta to the power n into Z to the power minus n. So if you start to simplify this, then it will be beta Z inverse whole to the power n, and it will be something like from minus n naught to infinity beta inverse Z to the power n. So here you are doing a change of indices. Earlier this was from minus infinity to plus n naught. Now you are making it from minus n naught to infinity. So therefore you are introducing a reciprocal term here, or a negative term here in the index n. So now it becomes beta inverse Z. Earlier it was beta Z inverse, now it becomes beta inverse Z, because you are introducing a negative term in the exponent, because you are changing this limits. All of you are able to understand what I'm saying?
Yes, sir.
Everyone is hearing me? Yeah. So you have introduced a negative sign here. So you can say that you have created a dummy variable n prime. That n prime is equal to minus n. Okay. So that will go from minus n naught to infinity. So that makes this beta inverse Z to the power n. So if the left hand side converges, that is if the series converges to a finite number, then it will converge only for mod Z less than mod beta. You can take this as a geometric progression, and the geometric progression will only converge when, so the geometric progression is like 1 plus r square plus r cube, like that, up to r to the power uh, as it goes on from 0 to infinity. And the closed form expression for the geometric progression is 1 by 1 minus r. So r is equal to beta inverse Z. So r has to be less than 1. So you can put that inequality beta inverse z should be less than 1. That gives you this particular condition. So we'll work out an example where I will show you this. So the path of integration again of the inverse z transform must lie in the region of the z plane inside the circle of radius mod beta. Earlier, for the other exponential, it was outside the circle. Now it will be inside this circle. So the ROC goes inside the circle. So we see that for the left hand side exponentials, complex exponential, the ROC is a disk with radius r, and it is the region inside the disk. Whereas for right hand side exponentials, complex exponential, the ROC is outside a particular r. So let us see the properties of ROC. ROC, or the region of convergence, consists of concentric circles centered at the origin in the complex plane. That is the idea. So always it is a concentric circle. Either it can be inside a circle, it can be outside a circle, or it can be annulus around the origin. So if the sequence has a rational Z transform, if x of n has a rational Z transform, rational means something that can be expressed as p by q, numerator by denominator, then the ROC does not contain any poles, and the ROC is bounded by poles or extends to infinity. So this is something to understand. ROC should not contain any poles. So the ROC is bounded by poles or extends to infinity. If the sequence X is finite duration, then the ROC is the entire complex plane except the origin or infinity. Again, I will show you an example. So we will look at this. It is just to like classify different types of ROC. If the sequence X is right-sided, we have already seen this, the alpha to the power n u of n minus n naught, something that is right-sided, then the circle mod z equal to r naught is in the ROC. Then all finite values of z for which mod z greater than r naught will also be in the ROC. So ROC will contain all points outside the circle. Again, if the sequence X is left-sided, that is something that I've shown you, beta to the power n u of n naught minus n. So here the circle, the ROC will be mod z greater than 0 less than r naught. So ROC will be inside the circle. And if the sequence is two-sided, that means you have both right side of the origin and the left side of the origin both exists for the sequence, then the ROC will consist of a ring that includes, or it will be mod z greater than r naught less than r1. So, uh, and both r naught and r1 are greater than 0. So it will be an annulus. So the ROC is an annulus centered at the origin containing the circle. Okay. So those who want to make a note, they can make a note of this slide, just to, because this summarizes the various kinds of regions of convergence that we can get. Okay, everyone is hearing me? Can all of you hear me?
Yes, sir.
Yes, sir.
Yeah, please. So those who are writing, they can make a note. Whenever you want to stop me, you can stop me. Okay? Whenever you feel like you want me to go to the previous slide, you can make me go to the previous slide. There is no problem. I will show all slides. Even in a previous topic, if you want me to talk about something, you can make me go there. Okay, who is coming now, Baba? Bhai Prakash, you are coming for this class or the next class?
Sir, I have been requesting for like from the beginning only, sir, but I haven't been admitted.
What? I have been doing it regularly for those who are requesting late. Anyway,
No, sir, this is like consecutive 4th to 5th time that I have requested you.
no problem. What can I do? Okay, so once you're finished, please let me know. What happened? It is done. Shall I move to the next slide?
Yes.
Okay. Some more points. So if the Z transform of X is rational and X is a right-handed sequence, then the ROC is the region outside the outermost pole, that is outside the circle of radius, equal to the largest magnitude of the poles of X. If X is a causal sequence, then ROC also includes infinity. This is generally what we will be working on. We will be using causal sequences. So we will have rational Z transforms, and we will have poles and zeros. So this point is the most important one. Most of the times we will be working with causal sequences. So the ROC will like you have to form the region outside the outermost pole, okay? Or that is outside the circle of radius equal to the largest magnitude of the pole of X. So the reverse case, if the sequence X is left-sided, then the ROC is the region inside the innermost non-zero pole. That is inside the circle of radius equal to the smallest magnitude of the non-zero poles of X. We'll look at examples and then we'll understand this better. So if X is anti-causal, that is a left-sided sequence, then the ROC also includes the origin. So as we had discussed, the ROC can be one of the following forms only: either a disk centered at the origin, possibly excluding the origin, or an annulus, or the exterior of a circle centered at the origin, and the entire complex plane, possibly excluding the origin and or infinity. So I'll illustrate this with some examples, and then the ideas will be more clear. So those who are writing, they can write. Okay, so one important announcement for all of you: we will have the class test next Thursday. Okay. So your class test will be next Thursday, and I will be taking the Tuesday class next week. So we will have 3 classes coming up, and whatever I can cover in those 3 classes will be included in the syllabus for the class test. Ideally, I should have held the class test in this week only. It is mentioned in the academic calendar, but because I had missed classes, so I am postponing it to the next week. On Tuesday only, I had the second vaccine, so that day I cannot teach. I was simply down in the bed. So last Tuesday I could not teach, so I am postponing the class test to Thursday next week. All of you are able to hear me? So you know now the date is like Thursday next week. So please make a note of it. This is a class test for 10 marks, and the syllabus will be whatever is taught before the date of the class test. Everyone?
It will be written test or
it will be written test. I will give you the question paper. We will have just like a small exam. You have done it in the last semester. No? Last semester was also online, isn't it? So I'll tell you the procedure, how to do it. And it will be like you have to write it on a piece of paper, and you have to scan it and send the piece of paper as a PDF file. So all that will happen. I will give you more instructions how it will be done. So all of you will be having a Google folder, and you will have to upload in the Google folder. I'll share a Google folder with everyone. Through ERP, I will send mails telling you like how to access that Google folder in my Gmail ID, and all of you have to confirm that you are able to access that Google folder. So once you are able to do it, then we will conduct the exam. I will put up the question paper on my screen, and you will work it out on a piece of paper, then take a picture of it and send it as a PDF. Okay. It will be almost like a proper exam. Okay, shall we move ahead? या बाबा यस और नो तो बोलो, कुछ तो बोलो, सबके सब चुप रहोगे तो कैसे होता है?
Yes, sir.
The bilateral Z transform of a causal signal. Let us start the examples. So how did we arrive at those ROCs? So the definition of the bilateral Z transform is this. So we are going to find out the expression of the Z transform, the closed form expression, when x of n is given as gamma to the power n u of n. Okay. So this is a causal exponential. How does it look like? It looks like this. This is x of n equal to gamma to the power n u of n. So this is a causal exponential, and the case we are analyzing is gamma equal to 0.85. So we start to form this right hand side. So the right hand side, if you express x of n as gamma to the power n u of n, then the lower limit becomes 0 to infinity, and it becomes gamma to the power n z to the power minus n. That is, it is gamma by z whole to the power n. So if you form the infinite series, then it looks like this. So it is a geometric progression, and it's, suppose I write this as the ratio r, then the geometric ratio r, then we can have a geometric progression like this, whose closed form expression is this, with the condition that mod of r is less than 1. So 1 by 1 minus r is the closed form expression for a geometric progression given like this, which is an infinite geometric progression, and mod of r is less than 1. So you apply this formula here, where r is equal to gamma by z. So you get 1 by 1 minus gamma by z. If you simplify this, this becomes z by z minus gamma, or 1 by gamma into z inverse. 1 by 1 minus gamma z inverse. That is what it becomes. So it is z by z minus gamma, and for this ROC should be gamma by z is less than 1, because here in this expression gamma by z should be less than 1. So if you simplify this, this becomes mod z than mod gamma. Okay. I hope this is clear.
Yes, sir.
This is how we derive the ROC for the causal exponential right-handed signal. So let us look at the picture. So these slides I have taken from BP Lathi. I'm telling you everything where I have taken my slides also. So those who want to read, they can read BP Lathi also. Again, PDF is available. So x of z exists only for mod z greater than mod gamma, and for mod z less than mod gamma, the sum will not converge but goes to infinity, because the denominator 1 minus 1 by gamma by z, that will tend towards infinity. So the ROC of x of z is the region in the z plane outside the circle of radius mod gamma centered at the origin. And since z is equal to gamma is the only pole of x of z, so mod z equal to mod gamma forms the boundary for the region of convergence. So poles cause non-convergent behavior. So poles are never found within the region of convergence. Okay. So this is important. So if you are done, then let me go to the next slide. We'll look at the other example. Once you have finished, let me know.
Yes.
So remember that the pole is not inside the ROC, okay? The ROC is mod z greater than mod gamma, not greater than equal to. It is always greater than mod gamma. Okay, so let us come to an anti-causal signal. So the anti-causal signal in the left-handed sequence, again minus gamma to the power n u of minus n minus 1. How does it look like? It looks like this. Starts from minus 1. It is u of n minus 1, minus n minus 1. So u of minus n means left-handed unit step sequence, and it's starting from u of minus n minus 1. So starting from here. So earlier I had used the notation alpha to or beta to the power n u of minus or n naught minus n. So here it is something like minus n plus n naught. N naught is equal to minus 1. Okay, if you want to be consistent with my previous notation, beta to the power n u of n naught minus n. That was the left-handed complex exponential which I had shown. So here it is like this, and it is minus. So that means this sequence is all having negative numbers. It is minus gamma to the power n. Okay. So this is an anti-causal exponential for the case gamma equal to 0.85. So because u of minus n minus 1 is equal to 1 for all n less than equal to minus 1. So the double limits will be like the limit infinity to plus infinity will be now minus infinity to minus 1. And what you are summing is minus gamma by z whole to the power n. So if you start expanding this, it comes like this. Okay. So again, you see there is an inversion here, z by gamma. So you are like taking n prime equal to minus n and making this index as 1 to infinity. That's why there is an inversion here. Or if you put n equal to minus 1, this will become inverse. Okay. So whatever you want, the way you want to imagine. So the second series can be simplified as the third one, and you can put this third one in the geometric progression form 1 plus r square plus r cube like that up to infinity. So it will be 1 minus 1 by 1 minus r, where r is equal to z by gamma. If you simplify this, again this term comes out to be z by z minus gamma. If you see the closed form expression of y of z, it is the same as this. Are you able to see this? For both these
Yes, sir.
sequences, x of n, the z domain expression is the same, it is identical. That's why I said the Z transform is like a lock and a key. So the Z transform expression is like the lock. So the key is different, and the ROC is the thing that will make the difference. Okay. So the ROC is different. For an anti-causal signal, the ROC is inside a circular region. So Z transform of both the causal and the anti-causal signal, the closed form expression is the same, but the region of convergence are different. And only with this information of the ROC you can find out what is x of n. Otherwise, you will confuse. Okay. So if you are done, then I will move to the next slide.
Sir, we have another class.
Yeah, understand. This is the last slide. Okay. So with this, I will stop for today. So we'll meet on Monday. Okay, fine. Go ahead.